Between Mars and Jupiter lies the asteroid belt, often imagined as a chaotic minefield of drifting rocks. In reality, it's almost empty. You could cross it and never see a single asteroid with your own eyes. Yet this quiet region holds a haunting secret. By every model of planetary formation, there should have been a planet here. Instead, more than 99% of that material is gone. Where did it go? And how did its disappearance shape the worlds we now call home? Sometimes the best way to absorb the mysteries of space is to let your mind drift among the stars. I'd be grateful if you'd subscribe and softly support the video. Now, let me paint you a picture of our solar system as it exists today. The asteroid belt stretches across a distance equal to the space between Earth and the Sun, 93 million miles of cosmic real estate. To grasp that scale, if Earth were a marble sitting in New York City, Mars would be another marble in Philadelphia, and Jupiter would be somewhere past Cleveland. The asteroid belt. It's everything in between Philadelphia and Cleveland. Now, scatter a few million grains of sand across that entire distance. Highways, forests, cities, farmland. And you're starting to understand how empty this belt really is. Calling it a belt feels misleading, like calling the Sahara Desert a beach, because both have sand. The average distance between asteroids runs into hundreds of thousands of miles, sometimes millions. When NASA sends spacecraft through this region, mission planners don't chart evasive courses or program dodge maneuvers. The Dawn probe spent 7 years crossing what we imagine as a cosmic demolition derby and encountered nothing but silence, vacuum, and the occasional distant glint of reflected sunlight hours or days away. Over a dozen spacecraft have made the journey. Not one needed to swerve. Not one came close to an unplanned encounter. This emptiness makes more sense when you look at the actual numbers, though the numbers themselves create their own kind of vertigo. Scientists estimate between 1 and 2 million asteroids larger than 1 kilometer across live in the belt, with maybe 100 million more if you count everything down to boulder size. That sounds crowded, the way a city sounds crowded when someone tells you 8 million people live there. But cities pack those 8 million people into a few hundred square miles. The asteroid belt packs its 100 million objects into a volume of space, roughly 3 billion cubic miles. Distribute those 100 million asteroids evenly, and each one gets a cube of space about 30,000 miles on each side, more than 3 times the diameter of Earth. Every single asteroid sits alone in its own Earth-sized bubble of nothing like houses in a neighborhood where each property line extends farther than the distance from Los Angeles to New York. You could stand on one asteroid, scan the sky with the most powerful telescope ever built, and the nearest neighbor would appear as nothing more than a faint dot if you could find it at all. The total mass tells an even stranger story, one that shifts the belt from merely empty to almost absurdly sparse. Every asteroid combined from Ceres, the dwarf planet that dominates the belt, down to the smallest tracked fragment, adds up to about 3 to 4% of the moon's mass. Think about that for a moment. Our moon, already tiny compared to Earth, you could fit 50 moons inside our planet, contains more material than this entire region, spanning the distance between 2 planets. It's like discovering that all the buildings in a major metropolitan area, when added together, weigh less than a single suburban house. A zone of space vast enough to hold the orbits of Mars and Jupiter, wide enough to fit more than 100 Earths, laid side by side, contains less rock than the grey sphere you can see with your naked eye on a clear night. If you could somehow gather every asteroid into one place, compress them all together, the resulting object would be smaller than our moon and would fit comfortably inside the distance between Earth and its lunar companion. The belt isn't a ring of debris, it's a whisper of what should have been a shout. Which raises the obvious question, where did everything go? The belt sits near what planetary scientists call the frost line, the boundary in the early solar system where temperatures dropped low enough for water to freeze into ice. This should have been prime real estate for planet formation, a region rich in both rock and ice, the building blocks of worlds. Simulations of the primordial solar system run on computers modeling the physics of gravitational collapse and dust accumulation suggest there was enough mass in this region to build a planet several times larger than Earth. Not a collection of fragments tumbling through the void, but a proper world with enough gravity to pull itself into a sphere to generate internal heat. From the compression of its own weight to possibly develop an atmosphere and magnetic field, a sibling to Earth and Mars, perhaps even larger, perhaps even capable of holding on to water. Instead, what remains is rubble, millions of fragments, none wider than the distance from New York to Chicago, most far smaller. They're scattered through a region of space so vast it's hard to grasp, like dust spread across an entire continent. Some was ejected entirely from the solar system, flung into interstellar space by gravitational interactions with the giant planets. These fragments now drift in the darkness between stars, orphaned from the sun, cooling slowly over billions of years until they match the temperature of the cosmic background radiation itself, about -270 degrees Celsius, just a few degrees above absolute zero. They'll drift forever, lightless, silent, carrying no record of their origin, except in their chemical composition, which no one will ever read. Some fell inward, consumed by the sun during the chaotic early epochs, when planetary orbits were still stabilizing, when the whole inner solar system resembled a game of cosmic billiards, played with objects the size of moons. These fragments added their mass to the sun's outer layers, a fraction of a percent, undetectable in the grand scheme of a star that fuses 600 million tons of hydrogen into helium every single second. They burned, or rather they joined the burning, becoming part of the light that now warms Earth. And some, perhaps the most important, some at least from our perspective, was delivered to the inner planets. Around 4 billion years ago, the inner solar system experienced what astronomers call the Late Heavy Bombardment, a deluge of asteroids and comets that rained down on Mercury, Venus, Earth, and Mars with a violence hard to fathom. The Moon's surface still bears the scars, vast impact basins, like the Sea of Tranquility, dark plains of frozen lava that filled craters so large you can see them from Earth with your naked eye. Craters stacked upon craters, overlapping impact sites, creating a palimpsest of destruction, a record written in melted rock and shattered crust that has remained unchanged for billions of years. Because the Moon has no weather, no tectonics, no processes to erase the past, Earth experienced the same bombardment, but unlike the Moon, our planet has weather, tectonics, and oceans that erase evidence. The craters are gone, buried under continents, or dissolved into the sea, subducted into the mantle, and recycled into new rock. But the material remains. Some of the iron in your blood arrived aboard an asteroid 4 billion years ago. Some of the calcium in your bones came from a fragment that crossed the orbit of Mars, fell through Earth's early atmosphere as a streak of fire, and buried itself in the crust of a planet that had only recently cooled enough to hold solid ground. The water in your cells might have spent its first billion years locked in ice on an object that formed beyond Jupiter's orbit, only to be scattered inward by gravitational chaos and delivered to Earth in a cosmic care package we never ordered but desperately needed. Even accounting for what fell into planets and what escaped the solar system, the math doesn't fully add up. The belt is too empty, too thoroughly swept clean. Something violent happened here, something that didn't just scatter the existing material but actively prevented a planet from forming in the first place. Something that turned what should have been a slow, patient accumulation of matter into a grinding machine that destroyed every building block before it could grow large enough to matter. The current theory points to a culprit most people don't think much about when they picture the solar system's early days Jupiter, the giant planet 318 times more massive than Earth, with a gravitational pull so strong it shepherds comets, deflects asteroids, and holds more than 60 moons in orbit. Didn't just sit peacefully in the outer solar system watching smaller worlds take shape. It became a weapon, and the asteroid belt became its first victim. But Jupiter didn't destroy the belt by smashing into it or by pulling it apart directly. The mechanism was subtler, more insidious, and far more effective. Jupiter killed the asteroid belt by simply existing in the wrong place at the wrong time and by refusing to stay still. Jupiter formed fast. Planetary formation usually takes tens of millions of years. A slow accumulation of dust into pebbles, pebbles into boulders, boulders into planetesimals, and finally planetesimals into planets. But Jupiter didn't follow the usual script. Within the first few million years of the solar system's existence, a blink of an eye on cosmic timescales, Jupiter had already grown massive enough to start influencing everything around it. By the time Earth was still a collection of moon-sized objects smashing into each other, Jupiter was already a giant, already pulling on every piece of nearby matter with gravitational fingers that reached across millions of miles. The belt sits between Mars and Jupiter, which means it sits in Jupiter's gravitational neighborhood. And living next to Jupiter is like living next to a neighbor who plays music so loud the bass shakes your walls, rattles your windows, and makes it impossible to think straight. Except, instead of sound waves, Jupiter generates gravitational waves, perturbations in the fabric of space-time itself that tug on every object within reach, accelerating them, changing their orbits, sending them on chaotic trajectories that cross and recross each other like highways with no traffic. Laws. In a normal planetary nursery, objects collide gently. A boulder drifting through space, at a few meters per second, bumps into another boulder, and if the collision is slow enough, they stick together. Friction and the weak electromagnetic forces between dust, grains, and small rocks do the rest. Over time, over millions of gentle collisions, these objects grow. A meter becomes 10 meters. 10 meters becomes 100. 100 becomes a kilometer becomes 10, and at that point gravity starts to take over. The object pulls in more material not because of sticky collisions, but because its own mass creates a gravitational well that nearby objects fall into. This is how planets form. Slowly, patiently, one gentle collision at a time. But Jupiter changed the rules. Its gravity stirred the region that would become the asteroid belt, accelerating objects to collision speeds, measured not in meters per second, but in kilometers per second. At those velocities, impacts don't build worlds, they destroy them. Two rocks slamming together at 5 kilometers per second, 11,000 miles per hour, faster than a bullet, faster than anything humans have ever built except spacecraft leaving Earth's gravity don't stick. They shatter. They vaporize on impact. They break into smaller fragments, and those fragments collide with others at equally absurd speeds, creating even tinier pieces, grinding everything down instead of building it up. The belt became a demolition zone. Every potential building block was smashed before it could grow. Objects that might have accumulated into moon-sized bodies that might have developed enough gravity to pull in more material and start the runaway process of planetary formation were instead pulverized into gravel. And the gravel was pulverized into dust, and the dust was blown away by the solar wind or swept up by Mars and Jupiter, leaving almost nothing behind. But Jupiter's influence went further, and this is where the story gets strange, almost unbelievable, except that the evidence is written into the compositions and orbits of the asteroids that remain. Jupiter didn't stay put. The planet didn't form at its current distance from the Sun and sit there peacefully while the rest of the solar system sorted itself out. Instead, Jupiter migrated. It moved inward, drifting toward the Sun, like a wrecking ball on a slow, inexorable swing. This idea, known as the Grand Tack hypothesis, emerged from simulations in the early 2010s and has been refined by later observations of migrating gas giants around other stars. It suggests that Jupiter didn't form and stay put. Like many young planets, it was embedded in a massive disk of gas and dust, and that disk exerted drag. As Jupiter slowed, it didn't stop, it fell inward. Over a few 100,000 to a million years, it migrated from beyond the asteroid belt to somewhere near Mars's current orbit. A planet 300 times Earth's mass, moving through a region of forming worlds, unleashed total gravitational chaos, scattering nearly everything in its path. Some material was flung outward, some inward toward the young inner planets, and what remained became the asteroids we see today. Survivors stranded in a region too disturbed to ever form a planet. Then Saturn formed. As it grew, it locked into resonance, with Jupiter reversing the effect of the gas disk. Jupiter's inward fall stopped, turned around, and both giants migrated outward to their present positions. The entire journey took only a few million years, yet it permanently reshaped the inner solar system. The asteroid belt still carries the evidence, a mismatched mix of dry, rocky bodies from near the Sun and dark, water-rich objects from far beyond it, refugees forced into the same narrow stretch of space. These two populations shouldn't coexist in the same region. It's like finding polar bears and camels living side by side or discovering penguins nesting in the Sahara, but they do coexist because Jupiter's migration mixed them together. The inward leg of the migration swept up dry, rocky asteroids from the inner solar system and carried them outward. The outward leg swept up wet, icy asteroids from beyond Jupiter's orbit and pushed them inward. By the time the migration ended, the belt had become a cosmic refugee camp, a dumping ground for objects displaced from their homes, scattered and abandoned in a region that would never allow them to settle into anything more organized. By the time Jupiter settled into its current orbit, the damage was done. The belt's mass had been reduced by over 99%. What remained was too dispersed, too fast-moving, too gravitationally disrupted to ever coalesce into a planet. Objects that might have stuck together now collided at speeds that guaranteed destruction. The slow, patient process of planetary accretion had been replaced by a grinding machine that crushed every hopeful beginning before it could grow into something real. So the asteroid belt exists in a kind of frozen state, a planet that never was, never could be. Not because the ingredients were missing, but because the timing was wrong. Jupiter arrived too soon, grew too fast, moved too violently, and turned a nursery into a graveyard. Without Jupiter's migration, those materials would have stayed in the outer solar system, locked away beyond the frost line, inaccessible to the rocky planets closer to the Sunday. Earth might have remained a dry, lifeless rock, too hot to hold water, too barren to support the chemical complexity that life requires. But Jupiter's violence scattered those materials inward. The same process that destroyed the asteroid belt delivered life's ingredients to Earth. And that raises a question worth sitting with: if the belt's destruction was necessary for our existence. What does that say about the nature of creation itself? What does it mean that we owe our oceans, our atmosphere, possibly even our origins as living beings, to a catastrophe that annihilated an entire planetary nursery? The asteroids that survived Jupiter's rampage carry the memory of both stories: the planet that never was, and the planet that became home to beings capable of looking back and asking why. If you could sort every asteroid by composition, by the story locked into its chemistry, something unsettling would appear. The belt isn't one family. It's two populations that should never have formed side by side. Their differences aren't subtle. They're a record of displacement of objects torn from their birthplaces and forced into the same crowded orbit. Astronomers classify asteroids by how they reflect light, their color, and spectral signature. These aren't dry labels. They're fingerprints. They reveal where an object formed, how hot or cold it once was, whether it ever knew water or ice. And the two dominant types in the belt tell mutually exclusive stories. S-type asteroids are bright and rocky, made of silicate minerals like those in Earth's mantle. They're dry, stripped of volatiles, forged in the intense heat of the inner solar system where water couldn't survive. C-type asteroids are the opposite. Dark, carbon-rich, often carrying water and organic material they formed far beyond the frost line, in deep cold, where ice was abundant and chemistry could run wild. And yet today, these two incompatible populations orbit side by side, silent proof that the asteroid belt is not a place of origin, but a place of exile. In a normal, peacefully formed planetary system, you'd expect to find S-type asteroids close to the Sun and C-type asteroids far from the Sun, separated by the frost line like two countries divided by a border. You wouldn't expect to find them mixed together any more than you'd expect to find desert plants growing in the Arctic or ice-dependent organisms thriving in the Sahara. But in the asteroid belt, 75% of asteroids are C-type. Dark, carbon-rich, water-bearing objects from the outer solar system. The remaining 17% are S-type, bright, rocky, dry objects from the inner solar system. The rest are oddballs, mixtures, metallic cores of shattered protoplanets that don't fit neatly into either category. This mixing is Jupiter's signature. During its inward migration, Jupiter swept through the region where S-type asteroids were forming, scattering them, accelerating them, flinging many into the Sun or out of the solar system entirely. Some survived and were pushed outward into what would become the asteroid belt. During its outward migration, Jupiter encountered objects from beyond its orbit: C-type asteroids, icy bodies, primitive chunks of the outer solar system, and pushed them inward, depositing them in the belt like refugees fleeing a war zone. By the time Jupiter's migration ended, the asteroid belt had become what scientists politely call a mixing zone, a term far too gentle for what it really was. The belt became a dumping ground, a cosmic lost and found filled with objects that didn't belong together, stranded there by Jupiter's gravity rather than formed in place. And this isn't just theory. In 2020, Japan's Hayabusa 2 mission returned samples from the asteroid Ryugu, a dark carbon-rich C-type body. Those samples contained water locked inside minerals, organic compounds, including amino acids, and even prosolar grains material older than the Sun itself. Every chemical signature pointed to the same origin. Ryugu formed far beyond Jupiter in deep cold where ice and organics could survive. Yet today, Ryugu orbits in the inner solar system, crossing Earth's path. It's an exile scattered inward by gravitational chaos. Spectroscopy shows it's not unique. Many C-type asteroids in the belt share this same distant origin. S-type asteroids tell the opposite story. Bodies like Vesta are dry, rocky, and internally layered, formed in intense heat close to the young Sunday. Vesta even differentiated into core mantle and crust, a process that requires early heat and rapid formation. Side by side, these objects shouldn't exist together. Their coexistence is the fossil record of a solar system violently rearranged. Vesta managed both. It formed quickly within the first few million years of the solar system's existence, when those short-lived isotopes were still abundant. It grew large enough to melt partially to separate into layers to develop a basaltic crust similar to Earth's oceanic crust. And then the process stopped. Jupiter's migration stirred, the region accelerated, collision speeds, and prevented Vesta from growing any larger. It became a frozen embryo, a protoplanet that never finished developing a world, that started the journey toward becoming a full-fledged planet but was cut off midway. When NASA's Dawn spacecraft arrived at Vesta in 2011, after a journey of 4 years and 1.7 billion miles, it found a world that looked nothing like the dead, cratered rocks people imagine when they think of asteroids. Vesta has geology. It has lava flows. It has a gigantic impact crater near its south pole. The Resilvia Basin, 500 kilometers across and 20 kilometers deep, carved by a collision so violent it nearly shattered Vesta into pieces. That impact happened about 1 billion years ago, and it sent fragments of Vesta's crust flying into space. Many of those fragments eventually found their way to Earth. Scientists have identified a family of meteorites called HEDs, Howardites, Eucrits, and Diogenites that all originated from Vesta. You can find them in museums, small chunks of an asteroid's crust that fell to Earth as shooting stars, carrying direct evidence of Vesta's internal structure, its basaltic composition, its history as an almost planet. Vesta formed where it currently orbits or close to it, in a region warm enough for rock but too hot for ice. It's a native, not a refugee. And comparing Vesta to Ryugu, one rocky and dry, the other carbonaceous and wet, both orbiting in the same belt, reveals the full scope of what Jupiter's migration accomplished. It scrambled the solar system's geography. It took objects that formed under completely different conditions, in completely different temperature zones, and forced them into the same neighborhood. And then it left them there stranded, unable to escape or settle or become anything more than what they are, witnesses to a planetary system's violent adolescence. The belt's diversity goes beyond just S-types and C-types. There are M-types metallic asteroids made almost entirely of iron and nickel, likely the exposed cores of shattered protoplanets that were large enough to differentiate but were then smashed apart by collisions during the chaotic, early epochs. There are V-types, fragments of Vesta's crust basaltic rock blasted into space by impacts. There are rare types that don't fit any category, objects with compositions suggesting they formed under exotic conditions or were altered by processes we don't fully understand. And recently, observations from the James Webb Space Telescope, which began science operations in 2022 and has been surveying asteroids as part of its broader mission, have revealed something unexpected. Some C-type asteroids show spectral features consistent with water ice on their surfaces, not locked into minerals, but actually exposed, frozen, sitting on the surface, in a region where sunlight should have sublimated it away billions of years ago. The most plausible explanation is that these asteroids are rotating slowly enough or have surfaces rough enough that some regions remain in permanent shadow, cold enough to preserve ice for the entire age of the solar system. They're like cosmic freezers, preserving samples of the primordial solar nebula in their shadowed craters. This diversity makes the asteroid belt a kind of archive, a museum of the solar system's formation. Each type of asteroid is a snapshot of a different time and place in the early solar system. The S-types remember the inner solar system, the region close to the sun, where rock dominated and ice was impossible. The C-types remember the outer solar system, the cold frontier, beyond the frost line, where water and organics were abundant. The M-types remember violent collisions, the shattering of bodies that had begun the journey toward becoming planets. And all of them together, mixed and scattered and abandoned, in a region that was supposed to become a world remember the chaos of Jupiter's migration. But the belt isn't just a passive archive. It's still dynamic, still evolving, still shaped by forces that operate on timescales so long they're invisible to human observation, but become obvious when you look at the structure of the belt as a whole. And those forces, subtle and patient and relentless, are what we turn to next, because the belt's current shape, the gaps and clusters and resonances that define it, tell a story about gravity's long memory and the strange ways that even tiny forces repeated over millions of years can reshape entire regions of space. Destination 4, the survivors Ceres and Vesta, 3100 to 4300. Tone intimate, character-driven, energy medium, focused attention. Among the millions of asteroids, two stand apart. Not because they're the most unusual or the most mysterious, but because they're the most complete. They're the survivors, the objects that came closest to becoming planets that started the journey but were cut short, frozen in a state between rubble and world. Their names are Ceres and Vesta, and their stories are written in geology, in chemistry, in the features visible on their surfaces when spacecraft arrive to study them up close. Ceres dominates the belt in a way that's hard to overstate. It contains roughly 1/3 of the entire belt's mass. That might not sound impressive until you remember that the entire belt combined equals only 3 to 4% of the Moon's mass, which means Ceres alone accounts for about 1% of the Moon, and all the other asteroids, all million-plus objects, share the remaining 2 to 3%. Ceres is the belt's titan, the one object massive enough to pull itself into a sphere to qualify as a dwarf planet under the International Astronomical Union's definition, to exert gravitational influence on the smaller bodies around it. Ceres measures 940 kilometers across. That's large enough to have a differentiated interior. A rocky core surrounded by a thick mantle of water ice, with a thin crust on top. But unlike the icy moons of Jupiter and Saturn, which orbit far from the Sun and remain frozen solid, Ceres sits close enough to the Sun that its surface ice should have sublimated away long ago. Sunlight at Ceres' distance is weak, about 9 times dimmer than sunlight at Earth. But over 4.5 billion years, even weak sunlight adds up. Ice, exposed to vacuum, and even faint warmth, gradually turns directly into water vapor without melting molecule by molecule escaping into space. And yet, when NASA's Dawn spacecraft entered orbit around Ceres in March 2015, becoming the first spacecraft to orbit a dwarf planet, it found ice. Not just trace amounts buried in permanent shadow, but significant quantities confirmed by spectroscopic analysis and later by direct observation of bright spots on the floor of a crater called Okator. Those bright spots puzzled scientists at first. They were too bright to be ice, too reflective, too persistent, too localized. Further analysis revealed they were salt deposits, sodium carbonate, similar to baking soda, left behind when subsurface briny water, salt water, liquid water, beneath the frozen crust, percolated up through cracks, reached the surface, and evaporated, leaving the salt behind like the rim around a dried-up lake bed. The implications are staggering. Ceres isn't just a dead rock. It has, or recently had, a subsurface ocean. Liquid water kept from freezing by some combination of internal heat from radioactive decay, residual warmth from Ceres's formation, and the insulating effect of the ice mantle above. That ocean might still exist. The salt deposits in Okata crater are geologically young, less than 4 million years old, possibly much younger. In planetary terms, that's yesterday. It means Ceres was geologically active in the very recent past, and might still be active today, hidden beneath a crust of ice and rock that shields the ocean from our telescopes and instruments. This discovery reshapes how we think about where water can exist in the solar system. We used to think liquid water required a planet like Earth, large enough to hold an atmosphere close enough to the sun to stay warm, with tectonics and a magnetic field, and all the complex machinery that makes Earth habitable. Then we discovered moons like Europa and Enceladus orbiting Jupiter and Saturn, with subsurface oceans kept liquid by tidal heating, the gravitational squeezing they experience as they orbit their giant parent planets. But Ceres has no giant planet nearby to squeeze it. Ceres maintains liquid water through internal processes alone, which suggests that subsurface oceans might be common in the solar system, hiding beneath the crusts of objects we thought were frozen solid. But Ceres' story gets stranger when you trace its origins. Its composition, water-rich, carbon-rich, dark, matches C-type asteroids, the ones that formed beyond the frost line in the outer solar system. Ceres shouldn't have formed where it currently orbits. The temperatures in the asteroid belt, even 4.5 billion years ago, when the solar system was forming, were too warm for so much water ice to condense. Ceres almost certainly formed farther out, well beyond Jupiter's orbit, in a region where water ice was as common as rock. And then, during Jupiter's grand tack migration, Ceres was pushed inward, scattered like all the other C-type asteroids, and happened to end up in the belt instead of being flung into the sun or ejected from the solar system entirely. That makes Ceres a transplant, an immigrant from the outer solar system, carrying with it the chemistry and composition of its birthplace, but now living somewhere alien. It's the belt's largest refugee, and it holds within its ice and rock a record of conditions in the outer solar system. During the epoch of planetary formation, a record we can study, that spacecraft can visit, that might even someday be sampled directly by future missions. Vesta tells a different story. Where Ceres is water-rich and dark, Vesta is dry and bright. Where Ceres formed in the cold outer reaches, Vesta formed where it currently orbits, or very close to it in the warmer inner region of the asteroid belt. And where Ceres remained geologically quiet, a ball of ice and rock that never heated enough to melt completely, Vesta underwent a transformation that turned it into something resembling a miniature planet. Vesta is smaller than Ceres, 525 kilometers across compared to Ceres' 940, but it experienced intense internal heating during the first few million years of its existence. That heating came from the decay of aluminum-26, a radioactive isotope that was abundant in the early solar system, but has a half-life of only 717,000 years. By the time a few million years had passed, most of the aluminum-26 had decayed away, and objects that formed late or grew slowly missed out on this heat source. But Vesta formed early and fast accreting from the solar nebula quickly enough to incorporate large quantities of aluminum-26 into its interior. As the isotope decayed, it released heat, and because Vesta was large enough to insulate that heat, small objects lose heat quickly through their surfaces, but larger objects retain it. The interior grew hot enough to melt, not completely, but enough for differentiation to occur. Heavy elements like iron and nickel sank toward the center, forming a core roughly 220 kilometers across. Lighter rocky material floated upward, forming a mantle of olivine and pyroxene. And at the very top, magma reached the surface and solidified into a basaltic crust, the same type of rock that makes up Earth's ocean floors. When dawn arrived at Vesta in July 2011, it found a world with geology. The southern hemisphere is dominated by the Rheasilvia impact basin, a crater so large it's visible from Earth as a dark patch through powerful telescopes. The impact that created Rheasilvia happened roughly 1 billion years ago. We know the age from counting smaller craters that have formed inside Rheasilvia since then, a technique called crater counting that uses the accumulation of impacts as a kind of clock. The collision was violent enough to excavate down through Vesta's crust and into its mantle, exposing olivine-rich rock that had been buried beneath kilometers of basalt. The impact also sent fragments flying. Some of those fragments remain in orbit near Vesta, a family of smaller asteroids called Vestoids that share Vesta's composition and orbit. Others were flung farther, escaping the belt entirely, crossing the orbits of Mars and Earth. Over the course of 1 billion years, gravitational perturbations from Jupiter and Mars nudged some of those fragments into Earth-crossing orbits. Eventually, they fell through our atmosphere as meteorites. Scientists have collected these meteorites, the head meteorites named after the 3 main types, Howardites, Eucrites, and Diogenites, and studied them in laboratories. The Eucrites are pieces of Vesta's basaltic crust, formed from magma that cooled on the surface 4.5 billion years ago. The Diogenites come from deeper, possibly from Vesta's mantle, exposed by the Resilvia impact. The Howardites are mixtures, brecciated rocks formed from impact debris, a jumble of crustal and mantle materials smashed together and welded by the heat of collision. These meteorites give us direct samples of Vesta's interior. We can measure their isotopic compositions, their mineral structures, their ages, and every measurement confirms the story. Dawn's observations told Vesta is an embryo, a protoplanet that started the process of becoming a full-fledged world but was stopped before it could finish. If Jupiter hadn't migrated, if the asteroid belt had been allowed to continue accumulating peacefully, Vesta might have grown large enough to hold an atmosphere, to maintain volcanic activity for billions of years, to develop a magnetic field from its iron core. It might have become a small, rocky planet, a sibling to Mars or Mercury. Instead, Jupiter's migration stirred, the region increased collision velocities, and prevented further growth. Vesta stopped accreting, its surface cooled and solidified. Volcanic activity ceased once the internal heat from aluminum-26 decay ran out. And for the past 4 billion years, Vesta has remained essentially unchanged, a snapshot of what a planet looks like in its earliest stages of formation. The contrast between Ceres and Vesta is striking. Ceres large and ice-rich, possibly harboring a subsurface ocean representing the outer solar system's cold water-abundant frontier. Vesta smaller and rocky, differentiated and geologically evolved, representing the inner solar system's hot, dry past. Both orbiting in the same belt, both cut short in their development, both frozen in time by the same event, Jupiter's migration and the chaos it created. But they're not just scientific curiosities, they're accessible. Unlike the moons of Jupiter and Saturn, which orbit deep within their parent planet's radiation belts and require complex, expensive missions to reach, Ceres and Vesta orbit in the relatively benign environment of the asteroid belt. Dawn visited both, spending 14 months at Vesta and more than 3 years at Ceres before running out of fuel in November 2018. Future missions could return, could land, could drill beneath Ceres's crust to sample its subsurface ocean, or excavate Vesta's interior to retrieve fresh samples of its mantle. And if humans ever expand beyond Earth, if we build infrastructure in space, establish mining operations, create permanent settlements off-world, Ceres and Vesta will be prime targets. Ceres offers water, vast amounts of it, potentially millions or billions of tons locked in its icy mantle, enough to support human outposts for centuries. Water is the most valuable resource in space, not just for drinking, but for making rocket fuel split water into hydrogen and oxygen. Future craft traveling between worlds. Vesta offers metals. Its differentiated interior means it has a concentrated iron-nickel core, similar to Earth's core, but far more accessible. On Earth, the core is buried beneath 3,000 kilometers of mantle and crust, unreachable with current technology. Vesta's core is buried beneath only a few dozen kilometers of rock, shallow enough that future mining operations could conceivably reach it, extract the metal, and use it to build structures in space without having to haul the material up from Earth's deep gravity well. So Ceres and Vesta aren't just windows into the past. They're potential resources for the future, stepping stones in a possible expansion of human presence beyond the narrow confines of our home planet. But they're also reminders of how fragile planetary formation can be, how much depends on timing and chance, and the gravitational whims of giant planets. Ceres and Vesta came close to becoming worlds. They had the mass, the composition, the internal heat. They just didn't have enough time. And that raises a thought worth pausing on. If Ceres and Vesta, despite everything working in their favor, couldn't finish becoming planets, what does that say about how rare planets actually are? How much has to go right? The timing of formation, the absence of disruptive neighbors, the availability of material, the stability of orbits for a planet to successfully form. Earth exists because a million things went right. The asteroid belt exists because a few things went wrong. But the belt's story isn't finished. The forces that shaped it 4 billion years ago are still operating, still subtle, still patient, and they're quietly rearranging the belt even now in ways that will matter millions of years from now. Destination 5. The silent mechanisms, forces smaller than whispers. 4300 to 5430. Tone quiet, revelation building to insight. Energy low, medium, meditative but precise. Gravity is patient. It doesn't need to shout or smash or explode to reshape the cosmos. It works through accumulation, through repetition, through forces so small they're invisible to human perception but become undeniable over timescales measured in millions of years. And nowhere is this patience more evident than in the mechanisms that continue to shape the asteroid belt long after the dramatic events of planetary formation have ended. The belt appears static. Asteroids orbit the Sun in predictable paths, following the same ellipses year after year, century after century. Nothing seems to change. But zoom out, speed up time, watch the belt evolve over 1 million years instead of a human lifetime, and patterns emerge. Asteroids drift, orbits shift. Objects that seemed safely distant from Earth gradually spiral inward, crossing the threshold from harmless to potentially dangerous. And the forces driving these changes are so subtle, so nearly imperceptible, that it took scientists decades to even recognize they existed. One of these forces is called the Yarkovsky effect, named after Ivan Yarkovsky, a Russian engineer who proposed the idea in the late 1800s, but whose work was largely forgotten until it was rediscovered and confirmed in the late 20th century. The effect is simple to describe but profound in its implications. When an asteroid absorbs sunlight, it heats up. And when it cools down, particularly on the side that has rotated away from the sun into shadow, it emits that heat as infrared radiation. Radiation carries momentum. Not much, but some. And when the asteroid emits radiation, it experiences a tiny push, a recoil like a rocket engine firing at a power so low it's barely measurable. For a small asteroid, maybe 100 meters across, this push amounts to a force of a few micronewtons, about the weight of a grain of sand pressing down on your hand here on Earth. Applied to an object weighing millions of tons, it produces an acceleration of roughly 1/1000th of a meter per second. In human terms, that's nothing. Completely negligible. A rounding error so small it vanishes into the noise of measurement. But apply that force continuously for 1 million years, and the asteroid's orbit shifts by kilometers. Apply it for 10 million years, and the shift becomes hundreds of thousands of kilometers. Apply it for 100 million years, and the asteroid can migrate from a stable orbit in the belt to an Earth-crossing trajectory, from a distant, harmless object to a potential impactor. All because of the gentle, relentless push of emitted heat. NASA has been tracking an asteroid called Bennu for over 2 decades, using both ground-based telescopes and the OSIRIS-REx spacecraft, which visited Bennu from 2018 to 2021 and returned samples to Resultante, Earth in September 2023. Bennu is about 500 meters across, shaped like a spinning top with a surface covered in boulders and loose rubble, held together by gravity so weak you could jump off the surface and escape into space if you pushed hard enough. It's also on a trajectory that will bring it close to Earth in the year 2182, close enough that there's a small but non-zero chance, about 1 in 2700 of an impact. Scientists tracking Bennu's orbit have confirmed that the Yarkovsky effect is nudging it closer to Earth at a rate of about 284 meters per year. That's roughly the length of 3 football fields, which sounds like a lot until you remember that Bennu is currently tens of millions of kilometers from Earth. At the current rate, it would take tens of thousands of years for the drift to accumulate into a significant change. But the drift is real, measurable, and entirely caused by the asteroid heating up during the day and cooling down at night. The Yarkovsky effect also depends on the asteroid's rotation. If the asteroid spins quickly, the hot side doesn't have time to cool much before rotating back into sunlight. and the push from emitted heat is small. If the asteroid spins slowly, the temperature difference between day and night is large and the push is stronger. The direction of the push depends on which way the asteroid rotates. If it rotates in the same direction, it orbits the Sun. Prograde rotation, the push nudges it outward away from the Sun, expanding its orbit. If it rotates in the opposite direction, retrograde rotation, the push nudges it inward toward the Sun, shrinking its orbit. This means the Yarkovsky effect isn't random. It's predictable, calculable, and it creates patterns in the belt that scientists can observe. Certain regions of the belt show a deficit of slowly rotating asteroids in specific orbital configurations, because those asteroids have drifted away over millions of years, pushed by the Yarkovsky effect into different orbits or into resonances with Jupiter that ejected them from the belt entirely. Other regions show an accumulation of asteroids with similar rotations because those asteroids have drifted into a stable configuration where the Yarkovsky effect no longer changes their orbits significantly. But the Yarkovsky effect isn't the only subtle force at work. There's also the Yorp effect, named after Yarkovsky, O'Keefe-Radzievsky, and Paddock, the scientists who contributed to its theoretical development, which changes not an asteroid's orbit but its rotation. Sunlight hitting an irregularly shaped asteroid creates torques, tiny twisting forces, as different parts of the surface heat and cool at different rates. Over millions of years, these torques can spin an asteroid up or slow it down, changing its rotation period from hours to minutes or from minutes to hours. Some asteroids spin so fast they're on the edge of flying apart. Bennu, for example, rotates once every 4.3 hours fast enough that loose material on its surface, boulders, pebbles, dust, is barely held down by gravity. A small increase in rotation speed, and that material would start to lift off, floating away into space or settling into orbit around the asteroid like a miniature moon. Other asteroids spin so slowly they might take days to complete a single rotation, which maximizes the Yarkovsky effect and causes them to drift more quickly. These effects, Yarkovsky and Yorp, operate entirely through the interaction of sunlight and matter. No collisions required, no gravitational slingshots, just the patient, relentless pressure of photons hitting dust and rock, absorbed, re-emitted, carrying away infinitesimal amounts of momentum that add up to profound changes over geological time. And then there's Jupiter, still exerting influence 4.5 billion years after its migration reshaped the belt. Jupiter's gravity creates resonances, orbital configurations, where an asteroid's orbital period is a simple fraction of Jupiter's. For example, if an asteroid orbits the Sun 3 times, for every 1 time Jupiter orbits it's in a 3-to-1 resonance. And that means every 3rd time the asteroid completes an orbit, Jupiter is in the same position relative to the asteroid. The gravitational pull from Jupiter at that moment adds up, reinforcing itself, creating a repeated tug that gradually changes the asteroid's orbit. These resonances carve gaps in the belt regions where asteroids are conspicuously absent. The gaps are called Kirkwood gaps, named after Daniel Kirkwood, the American astronomer who discovered them in 1866 by plotting the distribution of asteroid orbits and noticing that certain orbital periods were missing. The 3-to-1 resonance, for example, corresponds to an orbital period of about 4 years and creates a prominent gap in the belt's inner region. The 5-to-2 resonance, with an orbital period of about 7 years, creates another gap farther out. Asteroids that wander into these gaps don't stay there. Jupiter's repeated gravitational tugs change their orbits, usually by increasing their eccentricity, the amount by which the orbit deviates from a perfect circle. A more eccentric orbit means the asteroid's distance from the Sun varies more over the course of its orbit, which can bring it closer to Mars or even Earth. Eventually, close approaches to one of the inner planets perturb the asteroid's orbit, further ejecting it from the gap entirely, either into a different region of the belt or into the inner solar system, where it becomes a DID, near-Earth asteroid. This process is slow. An asteroid entering a Kirkwood gap might spend millions of years there before the accumulated perturbations from Jupiter and Mars shift its orbit enough to eject it. But the gaps are real, observable, and persistent. Maps of the asteroid belt show them clearly regions where the number of asteroids drops to near zero, separated by regions where asteroids are abundant. The gaps aren't empty, but they're sparse, maintaining a steady-state population where asteroids drift in and are ejected at roughly the same rate. The gaps also serve as a kind of pipeline delivering asteroids from the belt to the inner solar system. Most near-Earth asteroids, with orbits that cross or approach Earth's orbit, originated in the belt and were delivered to their current orbits through a combination of the Yarkovsky effect and resonance with Jupiter. The Yarkovsky effect nudges an asteroid's orbit over millions of years until it reaches a Kirkwood gap. The resonance with Jupiter increases the asteroid's eccentricity, bringing it close to Mars. A close encounter with Mars perturbs the orbit further, bringing it close to Earth. And suddenly, an object that spent 4 billion years safely in the belt is now on a trajectory that could intersect our planet. This delivery mechanism operates continuously. Every year, a few asteroids drift into resonances and begin the long journey inward. Most eventually collide with the Sun or are ejected from the solar system entirely by close encounters with planets, but a fraction, maybe a few percent, end up on Earth-crossing orbits. Over the lifetime of the solar system, this process has delivered millions of asteroids to the inner solar system, creating a population of near-Earth asteroids that pose both a scientific opportunity and a potential hazard. The hazard is real but manageable. Surveys have catalogued about 95% of near-Earth asteroids, larger than 1 kilometer, the size threshold for an impact that could cause global climate disruption and threaten human civilization. None of the known large asteroids are on collision courses with Earth for at least the next century. Smaller asteroids in the tens to hundreds of meters range are harder to track, and we've probably only found about 30 to 40% of them. These wouldn't cause global catastrophes, but they could devastate cities or regions if they hit populated areas. The asteroid that exploded over Chelyabinsk, Russia in February 2013 was only about 20 meters across, and it released energy equivalent to about 30 Hiroshima bombs, injuring over 1,500 people with shattered glass from windows blown out by the shockwave. But the same mechanisms that deliver asteroids to Earth also make them accessible. Near-Earth asteroids are easier to reach than objects deep in the belt. They require less fuel, shorter travel times, and simpler mission profiles. Several missions have already visited near-Earth asteroids. NEAR. Shoemaker landed on Eros in 2021. Hayabusa returned samples from Itokawa in 2010. Hayabusa 2 returned samples from Ryugu in 2020. And OSIRIS-REx returned samples from Bennu in 2023. Each mission has revealed that asteroids are far more complex, far more dynamic than anyone expected. Bennu, for example, is constantly shedding material. OSIRIS-REx observed small particles being ejected from the surface, floating into space, some escaping entirely, and others falling back down in slow motion under Bennu's weak gravity. The cause isn't fully understood. It might be thermal stress, fracturing rocks, or impacts from tiny meteoroids, or volatile compounds sublimating from beneath the surface. But it means Bennu is active, changing, evolving, even though it looks like a dead rock. And this is the pattern across the belt. Nothing is truly static. Everything is in motion, shaped by forces that operate on timescales far longer than human history, but become visible when you watch closely enough, measure precisely enough, accumulate data over decades instead of years. The belt is a dynamic system balanced between creation and destruction, accumulation and erosion, stability and chaos. Asteroids drift in and out of resonances. They heat and cool, spin up and spin down, slowly migrate inward or outward. Collisions still happen, rare but inevitable, sending fragments into new orbits, creating new objects, eroding old ones. And all of this happens in silence, in the vacuum of space, governed by forces that care nothing for human timescales or human concerns. Gravity doesn't hurry, heat doesn't rush. The Yarkovsky effect will nudge Bennu closer to Earth whether we watch it or not, whether we care or not, whether we're here to observe it or not. The mechanisms are impersonal, indifferent, and absolutely reliable. They've been operating for 4.5 billion years, and they'll continue operating for billions more, long after the Sun swells into a red giant and incinerates the inner planets, long after the asteroid belt itself is scattered or consumed. But here's the remarkable part: we understand these mechanisms. We can calculate them, predict them, and in some cases even imagine ways to counteract them. If an asteroid is on a collision course with Earth, the same Yarkovsky effect that nudged it inward could be used to nudge it away. Paint one side of the asteroid white to change its thermal properties, and over decades, the altered heat emission shifts its orbit enough to miss Earth, or attach a small mass driver, a device that throws pebbles off the asteroid's surface using the recoil to slowly change its trajectory. The forces required are tiny. The time required is long. But the principle sounds subtle. Forces applied patiently can accomplish what brute force cannot. And that principle applies beyond asteroid deflection. It applies to understanding the belt's past, predicting its future, and recognizing that the same patient, subtle mechanisms that shape asteroids also shape planets, moons, comets, and everything else in the solar system. Gravity works slowly. Heat dissipates gently. Radiation pushes softly. And over time, these whispers accumulate into reshaping the cosmos. The belt's current structure, its gaps, its clusters, its diverse populations, is the result of 4.5 billion years of these subtle mechanisms operating without pause. And the belt's future will be written by the same mechanisms, patient and indifferent, continuing their work whether we observe them or not. But the belt's greatest impact might not be on its own structure. It might be on us. Because those same mechanisms that scattered asteroids inward, that nudged fragments into Earth-crossing orbits, that delivered rocky and icy bodies to the early Earth, those mechanisms might be the reason we're here at all. Destination 6, The Gift, Water, Life, and US, 5430 to 6800. Tone connecting deeply personal. Energy medium building to quiet revelation. Earth was born dry. This might sound strange given that 70% of the planet's surface is covered in water. Given that oceans define our world more than continents, given that every living thing requires water to survive. But the Earth that formed 4.5 billion years ago, condensing out of the solar nebula in the hot inner region close to the Sun, didn't have oceans. It didn't have lakes, or rivers, or ice caps. It was a ball of molten rock, glowing red-hot with surface temperatures high enough to vaporize any water that might have been present. The inner solar system during the epoch of planetary formation was simply too hot for water to exist as a solid or liquid. Temperatures in the region where Earth formed ranged from 700 to over 1,000 degrees Celsius, hot enough to keep silicate minerals molten, hot enough to bake away any volatile compounds, water, carbon dioxide, methane, ammonia that tried to condense from the nebula. Those volatiles existed farther out beyond the frost line, the boundary past the asteroid belt, where temperatures dropped low enough for water to freeze into ice. But inside the frost line, the inner solar system was a desert, and the planets forming there, Mercury, Venus, Earth, Mars, were built from dry, rocky material that had been stripped of everything except refractory elements like silicon, iron, magnesium, aluminum. So where did Earth's water come from? The question has puzzled scientists for decades, and the answer is still being refined, but the broad outline is clear: the water was delivered. It came from elsewhere, carried aboard objects that formed in the cold outer solar system and were then scattered inward by gravitational chaos. Primarily Jupiter's migration. Those objects, asteroids, comets, icy planetesimals, bombarded the young Earth during a period called the Late Heavy Bombardment, around 4 to 3.8 billion years ago, and in the process delivered not just water but organic compounds, the carbon-based molecules that would become the raw materials for life. The Late Heavy Bombardment wasn't a brief event. It lasted for hundreds of millions of years, a sustained barrage of impacts that reshaped the surfaces of every rocky body in the inner solar system. The Moon bears the most visible scars because it has no atmosphere or geological activity to erase them. The largest impacts created basins hundreds of kilometers across Mare Imbrium, Mare Serenitatis, Mare Tranquillitatis, visible from Earth as dark patches that early astronomers mistook for seas. These basins were carved by objects tens to hundreds of kilometers across, moving at tens of kilometers per second, releasing energies equivalent to millions of nuclear weapons. Earth experienced the same bombardment, but the impacts here had consequences beyond just cratering. Some impacts were large enough to vaporize entire oceans if oceans had already formed. Others ejected material into space with such violence that fragments of Earth's crust were flung into orbit, some of which eventually fell back down, others of which escaped entirely, becoming interplanetary debris. The bombardment was a catastrophe, a period of chaos that would have sterilized the surface repeatedly, making it impossible for life to gain a foothold if life had existed yet. But the bombardment also brought gifts. The objects that struck Earth weren't just dry rocks. Many were C-type asteroids, the dark carbonaceous bodies that formed beyond the frost line and were scattered inward by Jupiter's migration. These asteroids contained significant quantities of water, not as liquid, but as ice mixed with rock or as water molecules bound into mineral structures. When they impacted Earth, the energy of the collision vaporized the ice instantly, releasing water vapor into the atmosphere. Over time, over millions of impacts, the atmosphere accumulated enough water vapor to saturate. And when the bombardment finally subsided, when the rate of impacts decreased, the planet cooled. The water vapor condensed. Rain fell, and the oceans began to fill. Current estimates suggest that 30 to 50% of Earth's water came from asteroids. The rest came from comets' icy bodies from even farther out in the solar system, and from water that was already locked in minerals deep within Earth's mantle, released over time by volcanic activity. But asteroids played a crucial role, perhaps even the dominant role, in delivering the oceans we see today. And we can trace this delivery through chemistry, through isotopic signatures that act like fingerprints identifying where water originated. Water molecules come in different isotopic forms. Most are made of 2 hydrogen atoms and 1 oxygen atom, H2O, but a small fraction contain deuterium, a heavier isotope of hydrogen with 1 proton and 1 neutron instead of just 1 proton. The ratio of deuterium to hydrogen varies depending on where and how the water formed. Water in Earth's oceans has a specific deuterium to hydrogen ratio, and scientists can measure the same ratio in meteorites, fragments of asteroids that have fallen to Earth, and in comets observed by telescopes. The ratio in carbonaceous chondrites, meteorites that come from C-type asteroids, matches Earth's ocean water almost perfectly. The ratio in comets is typically higher, suggesting that comets, while they delivered some water, weren't the primary source. Asteroids, specifically C-type asteroids from the outer solar system, match the chemical signature of the oceans. They're the best candidate for where most of our water came from. And it's not just water. The same asteroids that brought water also brought organic compounds. The samples returned by Hayabusa 2 from asteroid Ryugu contained more than 20 different amino acids, the building blocks of proteins. These amino acids formed in space on the asteroid through chemical reactions between water, carbon, and nitrogen under conditions that had nothing to do with life. They're prebiotic organic molecules, the kind of compounds that when concentrated in warm pools or shallow seas on the early Earth, might have assembled into more complex structures, peptides, then proteins, then eventually the first self-replicating molecules that would become the ancestors of all life. The bombardment that brought water and organics to Earth also brought them to Mars, Venus, and Mercury, though the outcomes differed. Mars, smaller and with weaker gravity, couldn't hold onto a thick atmosphere. The water delivered by asteroids probably created an ocean in the northern lowlands, a body of water that might have persisted for hundreds of millions of years, but eventually the atmosphere was stripped away by solar wind. Mars lacks a stripped away magnetic field to shield it, and the water either froze into the ground or escaped into space. Venus, closer to the Sun, received water but was too hot to keep it. The water evaporated, accumulated in the atmosphere, and was gradually broken apart by ultraviolet light, with the hydrogen escaping into space and the oxygen reacting with surface rocks. Mercury, closest to the Sun and smallest of all, couldn't hold onto an atmosphere at all. Any water delivered by impacts was lost almost immediately. But Earth was in the Goldilocks zone, not too hot and not too cold, with enough gravity to hold an atmosphere and a magnetic field generated by its molten iron core to shield that atmosphere from the solar wind. The water delivered by asteroids stayed. It filled the oceans, evaporated, and rained down again, cycled through the atmosphere and the crust, and created the conditions necessary for life to emerge. The timing matters. The late heavy bombardment ended around 3.8 billion years ago. The earliest evidence of life on Earth, fossilized microbial mats, chemical signatures in ancient rocks that suggest biological activity, dates to about 3.5 to 3.8 billion years ago, shortly after the bombardment subsided. The connection is hard to ignore. As soon as the planet was habitable, as soon as liquid water could persist on the surface without being vaporized by the next giant impact, life appeared. Or at least, life left evidence of its existence that has survived to the present day. This suggests that life on Earth might have originated with the help of the very asteroids that bombarded it. The organic compounds delivered by impacts provided the raw materials. The water created the medium in which those compounds could dissolve, concentrate, and react. And the energy from impacts from volcanic activity from ultraviolet light drove the chemical reactions that assembled simple molecules into more complex ones, eventually crossing the threshold from chemistry to biology. We don't know the exact steps. We don't know whether life originated in a shallow tidal pool or in a deep-sea hydrothermal vent or on the surface of clay minerals or some combination of all three. But we know the ingredients came from space delivered by objects that formed in the cold outer solar system and were scattered inward by Jupiter's gravitational chaos. The same process that destroyed the asteroid belt, that prevented it from becoming a planet, also seeded Earth with the materials necessary for life. And this leads to a perspective that's difficult to sit with. We exist because of a catastrophe. The asteroid belt's destruction was Earth's creation. Jupiter's violent migration shattered a would-be planet and turned the belt into a graveyard. But in doing so, it scattered icy bodies inward, delivering the water and organic material that made Earth habitable. Without that chaos, Earth would likely be a dry, sterile world. No oceans, no life, no us. The connection is intimate. Some of the atoms in your body, the hydrogen in your cells, the carbon in your DNA, the oxygen you breathe once belonged to asteroids. They formed in the cold outer solar system, were flung inward by Jupiter, collided with Earth billions of years ago, and were recycled through oceans, atmospheres, and living organisms until they became part of you. Every sip of water may contain molecules older than Earth itself. Every breath may include atoms delivered by impacts 4 billion years ago. This is the belt's true legacy. Not the planet it failed to become, but the planet it helped create, a graveyard and a cradle. And the story isn't over. Even today, tens of thousands of tons of extraterrestrial material fall to Earth each year, mostly as dust, occasionally as meteorites. Each fragment is a messenger from the solar system's youth, carrying the chemistry and history that ultimately gave rise to life and to us. And each one reminds us that we're connected to the cosmos in ways that go beyond metaphor. We're made of stardust. Yes, the heavy elements in our bodies were forged in supernova explosions and scattered into space, eventually condensing into the solar nebula. But we're also made of asteroid dust, of comet ice, of material that survived the chaos of planetary formation and found its way to Earth just in time to become part of the story of life. The asteroid belt, then, is not just a region of space between Mars and Jupiter. It's not just a collection of rocks that failed to become a planet. It's a library, an archive, a repository of the solar system's history. It's a reminder that creation and destruction are not opposites but partners, two sides of the same process. It's evidence that catastrophe and opportunity are often the same event viewed from different perspectives. And perhaps most importantly, it's a mirror. When we look at the belt, when we study its structure and composition and history, we're looking at the conditions that made us possible. We're tracing the path of the water we drink, the air we breathe, the atoms that make up our bodies. We're following the thread that connects us to the solar system's violent infancy, to Jupiter's migration, to the scattering of icy bodies inward, to the bombardment that delivered oceans and organics to a young molten Earth. The belt is empty because we are full. It lost 99.9% of its mass so that Earth could gain the fraction of a percent it needed to support life. It failed to become a world so that we could become a world capable of looking back and understanding the trade. And that understanding carries weight. It means that when we look at asteroids, we're not looking at threats or resources or scientific curiosities, though they are all those things. We're looking at family, distant, ancient, scattered across millions of miles, but family nonetheless. The belt is where we came from in a very real and physical sense. The atoms in your body traveled through that region of space 4.5 billion years ago, part of the material that might have become a planet, but instead became part of us. So the next time you drink water, or feel rain on your skin, or watch clouds drift across the sky, you're experiencing the belt's gift. The water filling the oceans, the water cycling through the atmosphere, the water running through your veins. It crossed the frost line billions of years ago, locked in ice on a carbonaceous asteroid, and was delivered here by gravity and chaos and chance. The asteroid belt gave us the world we live in. It gave us the oceans that cover the planet. It gave us the organic compounds that started the chain reaction leading to life. And in doing so, it gave us the ability to look up, to study the cosmos, to trace the origins of everything. We are back to a region of space that never became what it was supposed to be. Perhaps that's the most profound realization: we exist because something else didn't. The belt's failure is our success. Its emptiness is our fullness. And the story of those scattered rocks tumbling through the void between Mars and Jupiter is in the end also the story of every living thing that has ever existed on Earth. We are the belt's children, born from its ruins, carrying its atoms in our bodies, living on a planet it helped create. And that connection, that deep, physical, undeniable connection, means that the belt's story is not separate from ours. It's part of the same story, the same thread, the same unfolding narrative of matter, organizing itself into planets and moons and asteroids, and eventually into beings capable of looking back and asking why. The asteroid belt is empty, but we are here. And those two facts are not separate. They're the same fact viewed from different angles. The belt is empty because it gave everything it had to make us possible. And we are here because it gave everything it had. That's the gift. That's the legacy. That's what remains when you gather all the fragments and tell the whole story. A region of space that failed to become a world, but in failing made another world possible. A graveyard that became a cradle. An ending that was also a beginning. And we, standing on a planet covered in water that fell from the sky as rain 4 billion years ago, delivered by asteroids scattered inward by Jupiter's chaos, we are the proof that sometimes the most important stories are not about what succeeded, but about what failed and what came from that. Failure. The asteroid belt is a monument to failure, but it's also a monument to the fact that failure under the right circumstances can create something far more meaningful than success ever could. It can create oceans. It can create life. It can create a species capable of understanding finally where it came from and why. And that understanding, more than any ocean, more than any atom, is the belt's true gift to us, the knowledge that we are not separate from the cosmos. We are part of it. We are made of it. And the story of its past is also the story of our present. The belt failed to become a planet, but in doing so, it helped create a planet where beings could exist who would one day look back across 4.5 billion years and understand the connection. That's not failure. That's something else entirely.